Now try to see the scenario here. The second process that we are going to study is what? Constant pressure process. The second process that we are going to study is what? Constant pressure process. So give the heading constant pressure process. Another name for constant pressure process is what? Isobaric process. Constant pressure process or isobaric process. So what is constant pressure process or isobaric process? In that a point that we are going to study is what? A condition. Now what is condition? Condition is what? Here pressure is constant, or we can say P1 is equal to what we can say P2, or
Yes.
P2 by P1 is equal to what we can say? What we can say? P2 by P1.
Constant.
P2 by P1 is equal P1 P constant, P1 is equal to P2, or P2 by P1 means what? 1. Now then B point, equation of state. What is our generalized equation of state?
So equation of state is
Generalized.
V1 by T1
P1 V1 by T1
is equal to P2 V2 by T2.
P2 V2 by T2.
T2.
So if you observe the scenario here P1 and P2 is the same. So can we cancel P1 and P2? So
Yes,
what
sir.
we will become?
V1 by T1 is equal to V2 by T2.
V2 by what?
T2.
T2. So please write down this discussion, condition and equation of state. Please write down this discussion. Now our C point will be what? PV diagram. And
PV
what we
diagram
discuss?
and TS diagram.
So what we discuss? PV and TS diagram, generally not a compulsory, but generally PV and TS diagram must be side by side. So first of all, I am going to draw here axis for PV diagram, and similarly axis for what? TS diagram. So here we will have a pressure volume diagram, and here we will have a temperature entropy diagram. So when discussing pressure volume diagram, when we are going to discussing pressure volume diagram, here pressure is constant. As the pressure is constant, so how will be the PV diagram?
So it will be the horizontal diagram, line.
So it will be what? A horizontal line, because our pressure is a constant. Here we will have a two scenario. In one scenario, just observe.
Yeah.
This is one scenario.
Yes, sir.
And there is another scenario that is the reverse of this scenario. What is the basic difference between these two scenarios? Can you tell me?
So one is heat addition and one is heat rejection.
Okay, before that, before the heat addition or heat rejection, what is the first basic difference? In this scenario, what is happening? What is happening in this scenario?
That is a work. This is related to work.
No, here volume is increasing in 1 to 2.
Yes, volume is increasing.
And in this 1 to 2, what is happening?
Volume is reducing, decreasing.
Volume is decreasing. So whenever, so out of this one heating or cooling scenario, this volume increasing scenario, this one, first one, this above one, heating or cooling scenario, out of this.
This will be heating.
Because of the heat addition, what is going to happen?
Volume will increase.
So this is what our heating scenario. And heating means what? Heat addition.
Yes.
This is what a heat addition scenario. And second scenario will be what?
Cooling. That
Cooling
will be heat
scenario.
rejection.
And that cooling scenario means what?
Heat rejection.
Heat rejection. Now then, due to heat addition, what is going to happen with the entropy? Due to heat addition, what is going to happen with the entropy? We have studied in our
entropy will increase, sir.
Entropy will increase, and due to heating, temperature will also increase in case of the constant pressure. So how will be the curve? temperature
it will
and
be just like a curve which is following. Yes.
It is going up.
Yes.
Here temperature
Yes.
and entropy.
Yes.
Temperature and entropy both is increasing. So
Yes,
this is
sir.
what our heating scenario.
Yes.
Heating scenario means what? Heat
Addition.
Heat addition scenario. Now
Yes.
then a reverse of this one. What will
Yes,
be the
will be
reverse of
cooling
this?
or heat
This reverse
rejection.
of scenario. 1 to what? 2. So this scenario will be what?
This will be cooling or heat rejection.
Cooling scenario. And cooling
Yes.
scenario means what?
Heat rejection.
Heat rejection.
Perfect.
Okay, are you getting my point? So before
Yes,
going
perfect.
further, please draw this PV and TS diagram.
Yes.
So this is what our PV and TS diagram.
Yes, sir.
So this is what our PV and TS diagram. Now just
Yeah.
observe the scenario. If you remember our discussion from the last lecture, what we have seen, the similar PV TS diagram means not a PV. Similar TS diagram we have seen for the constant volume also. If you
Yes,
remember
yes.
constant volume, see the constant volume process. Similar TS diagram is there. Similar TS diagram is there. But
Yes.
suppose in exam it is not a, there is only one process is not there. It is a combination of the constant volume or constant pressure. Means suppose I'm going to take a one example here. Just see. I'm going to take just one example. Through that
Okay.
example you will get a more detailed idea. Suppose there is a one first process is what? Just 1 minute. Observe the things here carefully. So just imagine that here first process is what? A constant volume process. Constant volume heating. So constant volume heating means what? A straight vertical line upward. So this
Okay.
is what? A 1 to 2.
Okay.
So this is what our 1 to 2 process. After 1 to
Yes.
2, there will be 2 to 3 process is what? A constant pressure heating. Just now we have seen. So
Okay.
for PV diagram it is a no problem.
Yes.
But how to deal with the TS diagram? In this case, so see the things here carefully. Here what we can say, if you extend this line dotted line further, and we are going to make it as a what? 1 minute. We are going to make it as a dotted. So what we can say? V1 is equal to V2, can we say?
Yes.
And here suppose we extend this line further. So what we can say here?
P1.
So what we
P2
can
is equal to P3.
So what we can say here?
P2
P2 is equal
P3.
to
P3.
P3. So then what is going to happen here? On this TS diagram, observe the things here carefully. So observe the things here carefully. So TS. So now remember, see, now we have seen TS diagram for the constant volume process and constant pressure process is approximately same. But in this scenario, we have to differentiate that too in case of the TS diagram. So now
Yes.
remember, slope of the constant volume process is always higher. See this one, huh? Slope of the constant volume process. So this is what our constant volume process. Slope of
Yes.
the constant volume process is always higher as compared to constant pressure process. What is my
Okay.
point want to say? Slope of what?
Constant volume pressure
process.
constant volume will be higher compared to
Constant pressure process on a TS diagram. So here
Okay.
see, so higher slope means more towards vertical, higher slope.
Steep, little bit steeper.
Okay. And here for constant pressure process, 2 to
Okay.
3, slope will be what? Less.
Less.
And now you will say, sir, why is it like that? If you observe this scenario, in case of the constant pressure process, is there any motion there? In case of the constant volume, sorry, my mistake. In case
Yeah.
of the constant volume process, is there any motion?
No motion.
So motion is not there. So whatever the heat addition we are doing, where it is going?
It will increase the volume and increase
No volume will not increase na in case of the constant volume.
Yes,
So
yes,
whatever
yes,
the
yes.
suppose we are whatever the heat addition we are doing, where it is going? It is going into the internal energy.
Yes.
So here as and temperature of the object means temperature of the system is depends on what? Temperature of the system is depends on what? Internal energy. If higher internal energy,
The
then
temperature is more.
temperature is more. So if you are adding the heat and that entire heat is going where? Because of the no motion, where it is going?
Inside the system.
Suppose we know first law relation. What is first law relation? Q minus W is equal to delta U. Now
Delta
Q
U.
will become, what is the relation of Q? We can say delta U plus
Yes.
W. So here
Yeah.
W is what?
Work done.
Work
It
done,
is
it is
zero.
0. So Q will equal to what? Delta U. So
Delta U.
whatever heat we are adding, where it is going? Going into the change in internal energy.
Internal energy of the system.
Okay. As internal energy means whatever the heat addition we are doing, it is going directly to the what? To the heat transfer. And as it is going directly to the heat transfer, what is going to happen? As it is going directly, okay, going to the internal, as heat transfer is going into the internal energy directly, no work is there. So because of that, our temperature increment rate is higher. Here if you
Okay.
observe, temperature increment rate will be what here in this scenario? Higher
Higher.
as compared to constant pressure process, because in constant pressure process there is a work done also. So means
Yes.
our Q will going into the two things. Means our
Okay.
Q will going into the what? Change in internal energy in case of the constant pressure and work done.
And work
And
done.
so that's why temperature increment rate is lesser in constant pressure as compared to constant volume. You got the reason also?
Yes, sir.
Okay. So now before going further, just draw this example. So that means it is a combination of what? Here process 1 to 2 is what? Constant volume heating. Process 2 to 3 is what? Constant pressure heating.
Yes. सर ये एग्जाम्पल में आफ्टर फिनिशिंग दिस पार्ट ना उसके बाद में बना दूं
Which one, sir?
सर दिस एग्जाम्पल व्हाट यू हैव गिवन ना
No. Just below that drawing.
जस्ट बिलो दैट ड्राइंग
Yes. Don't have to draw after the writing all the things. Just after this drawing means here is the scenario I am explaining you. Two comparison of two processes. And we need
Okay.
it. Exam point of view these things. There are
Okay.
some few questions are there. First process constant volume, second process constant pressure.
ओके
Now try to see the next point here. What is our next point? What will be our next point? No, we don't need this discussion.
नेक्स्ट पॉइंट विल बी बाउंड्री वर्क रिलेशन
So try to see the scenario here. What will be the boundary work relation? That is our E point. Boundary work relation. Now meaning of boundary work means motion of the boundary means motion of the piston. Boundary work relation. So boundary work relation here will be what? P. V2 minus V1. Or another relation is what? MR. T2 minus T1 and unit will be in what? Kilojoule. Please write down this relation. Now our F point will be what? First law relation. What is first law relation? For closed system we have seen
Q minus W is equal to delta U.
Q minus W is equal to what?
Delta U.
Q minus W is equal to delta U. So Q will become what? Delta U plus W. Can you tell me what is the relation of delta U? M for change in internal energy for
Yes, sir. Wait. m into CV T2 minus T1.
m into CV T2 minus T1.
T1.
And just now we have seen relation of the work done.
Yes.
mr
T2 minus T1.
mr T2 minus T1. So what will become? Q.
Yeah, is equal to
Q is equal to what? We can take out a common. What we can take out? M
T2 minus T1.
We can take out common m T2 minus T1. And what will remain?
CV plus R.
And we have seen Cp minus Cv is equal to, we have seen what? R.
Yes,
so Cp will become what? Cv plus R.
Yes.
So can we replace Cv plus R by what?
Of course, sir.
By Cp. So m into T2 minus T1. Cv plus R is what? Cp. So Q will become what?
mCp
T2 minus
T1.
And it will be in what? Unit will be in what? Kilojoule.
Yes.
So this relation, above relation is used to find out what we can say. Above relation is used to find out. Above relation is used
to find out. The quantity of heat.
Is to find out. 1 minute. Is to find out heat transfer for constant pressure process.
Okay.
Whenever we want to find out heat transfer for constant pressure process, we are going to write down this relation. Now try to see the scenario here further, what we have to do and how we are going to approach the further. Now what is our last relation here? What is the G point?
G point is change in entropy relation.
What is the G point? Change in entropy relation. So our change in entropy relation, delta S will be what?
Delta S is equal to mCp.
Second one relation is what? Second relation of change in entropy for change in entropy for closed
system. Delta S is equal to m into Cp ln T2 by T1 minus R of ln R into ln V2 by V1. P2 by P1.
Minus R ln P2 by P1. Ln means what? Natural log.
Natural log, yes.
So if you observe here, what we will have? M Cp ln T2 by T1 minus R into what? Ln of what? What is P2 by P1 here? 1.
P2 by P1
1. So ln of 1. And what is the value of ln of 1?
0.
Ln of 1 is what? A 0. So this term will become 0. So what is the relation of change in entropy? Delta S for constant pressure process will be what? mCp ln T2 by T1. mCp ln T2 by T1. Please write down this relation. So this is all about our which process? That is what we have seen.
Constant pressure process.
Constant pressure process. Now what will be the next process?
So next will be isothermal process, constant temperature.
The third process that we are going to study, constant temperature process. So give the heading, constant temperature process
or isothermal.
Another name for constant temperature process is what?
Isothermal
process. Please give this heading.
Okay, sir.
Now here Our A point is what? Condition. What will be the condition here? We can say
T1 will be T is constant.
T constant.
Yeah.
Or we can say initial temperature is equal to what? Final temperature. Or final temperature divided by initial temperature is equal to what?
1.
Now then B point will be what? Equation of
state.
Our generalized equation of state will be what?
P1 V1 by T1 is equal to P1 V2 by T2. T1 and T2 are constant or same. Therefore, P1 V1 is equal to P2 V2.
So we can say as T1 T2 is the same, we can cancel them, and we can say at the end P1 V1 is equal to what? We can say
P2 V2.
P2 V2. So please write down this relation. Now our C point will be what? Pressure volume diagram, and D point is what? Temperature entropy diagram. PV diagram, and D point is what? Temperature entropy diagram. So how to deal with pressure volume diagram and temperature entropy diagram? See the things here carefully. Pressure volume diagram. Pressure volume diagram, and the next point will be what?
Temperature entropy diagram.
Temperature entropy diagram, that is what? TS diagram. Now how to deal with this one? Pressure volume and a temperature entropy. So what we have to do, and how we are going to approach the things further. So for pressure volume, see here we will have a two scenario. In one scenario we have a expansion, in another scenario we have a compression. So first of all we will see what is expansion. So this is meant by what? Here what is happening? Expansion or compression here. This scenario will be what? Expansion or compression? This scenario is what?
Expansion.
Expansion. So in expansion what is going to happen? Pressure is going to decrease, volume is going to increase. The second scenario will be what? Compression. So the second scenario will be what? A compression. In case of compression, what is going to happen?
Volume decreases, pressure increases.
So this is what our expansion scenario, and this is what our compression scenario. Now tell me here, what about heat addition? It is a heat addition in case of the expansion. In case of the expansion, is it a heat addition or heat rejection or Q0?
So expansion will be
in case of the
heat
expansion.
And compression will be heat rejection.
Compression will be heat rejection. Expansion is what?
Heat addition.
Expansion is heat addition and compression is what?
Heat rejection.
Can you explain me your point? Why is it like that? Can you explain me?
Because expansion, sir, whenever we suppose we consider the water, so whenever we are going to heat the water, the volume will be increasing.
Yes, that is what expansion, correct.
Yeah, but the pressure will reduce. No?
Yes, pressure is going to reduce, correct.
Yes. Similarly, in case of compression, if you are going to reduce the volume, then the pressure will increase.
Okay, what about temperature? What about heat addition or heat rejection?
Sir, in compression also the temperature will increase, yes.
In case of the compression, temperature will increase. But what is the name that we have given to the process? What is the name?
Constant temperature.
So then how it is possible to increase the temperature then? So try to see the scenario here for that purpose. Just observe how it is. Your answers are correct. What you said, in case of expansion, heat addition. In case of the compression, heat rejection. And with this example, we are going to understand. Suppose we are taking a piston cylinder arrangement. Just observe.
Yes.
This is what our cylinder. 1 minute, I will draw cylinder properly. So this is what our cylinder, and in the cylinder just imagine that we have a air, because we are everywhere, everything we are talking about ideal gas, and air is an ideal gas.
Yes.
So here we have a air in the cylinder. Just imagine that it is a air, and what we are doing, what we are going to do, we are going to compress this air. What is we have? We have a air, and we are going to compress the air. During the compression, what is going to happen? Work input or work output? During
Work
the
input, sir.
we are giving the work input. So during the
Yes.
compression, so this is what our compression scenario. In case of the compression, we are giving the work input. As we are giving the work input, a normal tendency is what? Normal tendency is what? Pressure is going to increase, volume is going to decrease, and inside
Yes.
temperature is going to increase. Temperature of the
Yes.
air is going to increase. But what is our target? What we want to do? What is our target? We have to keep the temperature constant. What is our target?
Yes.
We have to keep the temperature constant. And to make the temperature constant, which thing we can do? Heat addition or heat rejection?
Heat rejection.
You are getting my point. Then and then only temperature will going to remain constant. Otherwise, if you are not doing heat addition or heat rejection, what happen then? If you are not doing heat addition, if you are not
Then
rejecting
it
the heat,
satisfies the law.
means
The point
okay.
of constant temperature.
If you are not rejecting the heat, what is going to happen? Temperature of the air is going to what? Temperature
Increase.
of the air is going to reduce. Sorry, temperature of the air is going to increase. During the compression,
Increase.
normal tendency is what? If you are not doing any cooling, what is going to happen? Temperature of the air is going to increase. But we don't want increase in temperature of the air. And what we have to do for that purpose? We have to reject the heat. So what final conclusion we can say? In case of the isothermal compression, whenever there is a what, we will say isothermal compression. Isothermal compression means what?
Constant temperature.
What? Isothermal compression, heat addition or heat rejection?
Isothermal compression will be heat rejection.
So constant temperature, heat addition. But you got my point. Why it is a heat rejection? Because if you are compressing the air, temperature of the air is going to increase. But if you want maintain the constant temperature, then what we have to do? We have to reject the heat. Then and only then what is going to happen? Temperature of the air. Here this temperature of the air is going to remain constant. So this is what our isothermal compression. And isothermal compression means what? Constant temperature, heat rejection.
Heat rejection.
And
process.
in case of the isothermal expansion, it is the reverse of the. In case of the isothermal expansion, what is going to happen? Constant temperature.
The volume will increase. Yeah.
Constant temperature, then heat
Addition.
It is the reverse of the expansion. So
Yes.
in case this point is very very important. So in case of the expansion, what is going to happen? Heat
The
addition.
volume will increase, but the temperature will reduce.
In case of the expansion, heat addition. In case of the compression, what is going to happen?
Heat rejection.
Heat rejection. Now we will come to the TS diagram. Can you guess how will be the TS diagram here? Because temperature is constant here. How will be the TS diagram?
Sir, it will be a straight vertical line?
It will be what? Temperature constant.
No. It will be the horizontal line, sir.
So it is as a temperature constant. It must be what?
Horizontal line.
Horizontal line.
Yes.
So it must be what? A horizontal line. So what we can say here? 1 to 2.
Yes.
Now horizontal line. What is happening here? Tell me in this case what is happening? What is happening? Horizontal line. 1 minute. I will. And 1 minute. I will draw another line also. It is the reverse of this one. What is the difference between these two? What is the difference between these two? Top one and bottom one. Here what is
Sir,
happening?
over here,
In the
top 1 to 2, there is a heat rejection.
In 1 to 2.
Yes.
Is it a heat rejection 1 to 2? Because here entropy is increasing, na?
Yes. Entropy increases means temperature will rise, na, sir? energy
Temperature
is
and
taken.
see, remember one point. Temperature and entropy is not a. These are the two different things. When entropy is going to
Okay.
increase, temperature and entropy doesn't have anything. Doesn't have anything. When
Okay.
that's
Okay.
see here, what is happening here? Tell me. Temperature is constant, but here what is happening with the entropy? Tell me.
Entropy is increasing, sir.
So how they are then? It is not. They are not related. Entropy is depend on which two things? Tell me. Entropy is depends on which.
Entropy depends upon first thing is irreversibility.
And second thing is what? First thing is irreversibility.
Second thing is heat transfer.
Heat transfer. And in this chapter,
Yeah.
irreversibility is what?
Irreversibility is zero.
Irreversibility is zero. So only depends on heat transfer. In heat transfer, we have
Yeah.
two things. Which two things we have in heat transfer? In heat transfer, we have two things. Which two things we have?
Constant pressure, constant volume.
No, in heat transfer, we have two things. In case of the heat transfer, change in entropy, heat addition, heat rejection. Due to heat addition,
Yeah.
entropy is going to what?
Heat addition, entropy is going to increase.
So tell me here what is happening. Here what is happening. So this is what, a expansion scenario or a compression scenario? This one, this top one scenario. This top one scenario, expansion scenario or compression scenario? This top one.
Expansion.
Why expansion?
So entropy is increasing, the randomness is increasing.
So what? Why it is increasing randomness?
So the volume will be more, no?
No.
If the randomness is increasing.
No, that is not a volume, is not anything here. See, here entropy is increasing. When entropy is going to increase? Whenever we have a heat addition. And in case of the expansion, what is happening? Tell me. In case of
There
the
is heat addition.
heat addition, that's why this scenario is for what?
Expansion.
Because of why? For the expansion? Because here we are adding the heat. And that's why our entropy is increasing here. And why we are adding the heat? You got this point?
Yes.
But in this case, in case of the compression, what is happening? Here entropy is decreasing. And in case of the isothermal compression, what happened? Heat rejection is there. Just now, few minutes before we have seen. 1 or 2 minutes before we have seen. So in case of the compression, what is happening? Heat rejection. And due to heat rejection, what is going to happen to the, due to this heat rejection, what is going to happen? Due to heat rejection, what is going to happen to the entropy? Entropy is going to reduce, and here entropy is reducing. That's why this scenario is for what?
Compression.
Compression. And compression means what? Heat rejection.
Heat rejection.
Expansion means heat addition, and heat addition means what? Isothermal expansion means heat addition. Remember this point. Isothermal expansion means what? Heat addition. And that's why here what is happening? Entropy is what? Increasing. Isothermal compression means what? Heat rejection. And that's why here entropy is what? Decreasing. Please draw this drawing. After completing this drawing, draw this one also and write down this discussion. Draw this figure. So here what we are explaining. Here it is a compression is happening. So this is isothermal compression, isothermal expansion. Now the next thing will be what? What will be the next point? E point is what? What will be the
boundary
E point?
work relation.
Boundary work relation. What is our E point? E point is what? Boundary work relation. And how to get the relation for the boundary work? The most important relation here. Just little bit a tricky relation. We have to memorize this relation. MRT Means here we can say take a T1 or a T2 because both are the same here. So MRT ln of what? P1 in the numerator and P2 is in what? Denominator. So we can say MRT ln P1 by P2. You are getting my point?
Yes.
So this is what an important relation. This is what we have to memorize this one. From this relation we can derive a further relations also. So see, instead of MRT can we write down PV?
Yes.
So PV ln P1 by P2. Can we write down this
Yes.
one?
Yes.
Then instead of see this one, we will keep the PV like this ln of what? Now we have seen just in equation of state P1 V1 is equal to what we have seen for isothermal process P2 V2.
P2.
So P1
Yes.
by P2 what we can write down? V2
V2
by
by
V1. So can we replace P1 by P2 by what?
V2 by V1.
V2 by V1. So this is another relation. And the
Yes.
fourth relation for this one, instead of PV, what we can say? MRT ln of what? V2 by V1. And in every relation, what will be the unit of work done?
Kilojoules.
Kilojoule. So remember what we have to do here. We have to just memorize the first relation. All other relation we can automatically derive from this relation. Means MRT means PV. ln of P1 by P2 means what? P1 by P2 can be replaced by what? V2 by V1.
V2 by V1.
And here PV is what?
In this case,
Huh?
sir, this we have written 3 volume and 3 pressure. That is P and P1 and P2. So what is P? P will be the absolute pressure, and then what is P1 and P2?
See. If you see, you can say take here instead of PV, you can take it P1 V1. 1 minute, I want to explain you here. So you are here, you are saying P and V. Just we have taken PV. We have not written anything. So here you can take in place of PV, we can take either P1 V1 because that's what we have said now, or P2 V2. So instead of PV, we can take in place of PV, we can take a for 0.1 or we can take it for what? 0.2. Same for the MRT here because temperature is the same.
Okay.
So please write down this discussion. Now what is our F relation here? What will be the relation of F? What will be the relation of F? F is what?
First law relation.
Our F point is here what? First law relation. And what is first law relation?
Q minus W is equal to U, delta U.
Q minus W is equal to what?
Delta
U. And what is the basic relation of delta U? M for change in internal energy for an ideal gas we have seen. MCV T2 minus T1. And what is T2 minus T1 will be here? 0. So this term will become what? As T2 minus T1 is 0. So this term will become a 0. So what will become? Q minus W is equal to what? 0. And here Q will become what? W. So for isothermal process, whatever may be the heat transfer, means whatever be the work done, same will be the heat transfer. That is the basic rule. And that's why temperature is remaining constant. That means whatever we are adding the heat, that heat is going to the work expansion. Or whatever work input we are giving, that is going into the heat rejection. And that's why temperature is remain constant here. So please write down this one. Now our G point will be what? Change in entropy relation. Our G point is what? Change in entropy relation. Try to see the scenario here. So what is our change in entropy relation of first relation? Change in entropy for closed system containing an ideal gas. Generalized relation MCV ln
ln
T2 by T1
minus
plus first one plus R
plus R
into ln
V2 by V1.
V2 by V1. Now what will be the T2 by T1 here? What is the ratio of T2 by T1? 1. So MCV ln of 1. And what is the value of ln of 1?
0.
Ln of 1 value is what? 0. So can we make this term, this entire terms, this ln of 1 will 0. So this term will become what? 0. So what will be the change in entropy for isothermal process? Delta S will be what? M R ln of what?
ln of
V2 by V1. And it will be in what? Kilojoules
per kg Kelvin.
No, per Kelvin. If we are saying taking mass 1 kg, then per kg Kelvin. Otherwise, only kilojoule per Kelvin. If we are taking mass as a 1 kg, then we will say per kg Kelvin. So please write down this discussion for change in entropy relation. Now what will be our next process?
For the constant pressure.
So fourth one, what is our fourth process?
So we don't have to derive this for P in terms of P.
Yes. Here we will derive in terms of P also, correct. So my mistake is here. So in terms of P, what will be there? MR ln. Instead of V2 by V1, we can write down
P2 by P1. P2 by P1.
No, wrong, not P2 by P1. P1 by P2. P1 V1 is equal to P2 V2. So V2 by V1 will become what? P1 by P2, na?
Okay.
So see. So please write down this relation also.
So over here we have said that P1 by P2 is equal to V1 by V2 by V1. That's why what?
We have written, sir, for isothermal process, what is the relation? Tell me. P1 V1 is equal to P2 V2, na? Then V2 by V1 we can write down by what?
Sir, if I'm maybe I have committed a mistake, like the change of entropy of a closed system containing an ideal gas equation.
Okay.
There delta of capital S, that is delta of S.
Okay, 1 minute, I am coming back to that relation.
Yeah.
Okay, this is the relation, that is what you are talking,
Yeah. It is P2 by P1, na? ln of P2 by P1.
Minus ln of P2 by P1. But here we have a minus, na? Here we have a minus, na?
Yeah.
And if you, so suppose we make this term 0, then we will get what? Minus mr ln P2 by P1. And if you want to remove this minus sign, what will happen then? It will become P1 by P2, na?
Okay.
So it, suppose we make it this term, that is what your doubt, na sir, it must be P2 by P1. Minus mr ln P2 by P1.
Perfect.
Minus mr ln by P1, and if you want to remove this minus sign, this will become what? Raised to the power minus 1, basic maths.
Yes.
And raised to the power minus 1 will become what here? P1 by P2.
Perfect. Understood.
Okay. That's why, sir, here. But good discussion. So here we will have what? Unit will be in what? Kilojoule per Kelvin.
Kilojoules per Kelvin. Okay.
So now try to see the scenario here. What we have to do? What is our next process now? What is our next process? Fourth one is what?
Adiabatic process. Adiabatic.
Isentropic process.
Yeah.
And in this chapter, Adiabatic process is also what?
Isentropic.
Isentropic. So adiabatic process or isentropic process. So give the heading adiabatic process or isentropic process.
Done.
Now here what will be the our A point? A point is what? A condition. So here condition is what we can say. First situation, first condition we can say S1 is equal to S2 means
Yes.
or yes is we will say yes. Yes constant. Yes constant means what? Initial entropy is equal to final entropy, or
Yes.
delta S means what? Final
Is equal
entropy
to
minus final initial entropy will become what? 0. And second condition is what here? Why entropy is constant here? Because heat transfer is what? 0.
Okay.
So please write down this condition. Then B point will be what? Equation of state. Now
Yes.
here we will have a 3 equation of state. B point
Okay.
will be what? Equation of state, and here we have what? 3 equation
A1,
of.
B1.
Okay. So no, first of all what? Try to see the scenario here. We are not deriving it from generalized. First equation of state is what? P1 V1 raised to the power gamma is equal to what? P2 V2 raised to the power gamma. What is meaning of gamma? Tell me.
So gamma was the constant of
Okay, what is gamma? What is mean by what gamma? We have seen earlier in the beginning of this chapter. We have seen gamma. What is mean?
adiabatic index or
Or
isentropic
isentropic
index.
index. Correct. And why we have given that gamma means adiabatic index or isentropic index? We are because we are using gamma for the isentropic process or adiabatic process index for that process. Then next relation of equation of state is what? T2 by T1 will be equal to what? P2 by P1 raised to the power what? Gamma minus 1 by what?
Gamma.
Gamma. And third relation will be what? What will be the third relation? T2 by T1. See this one. Third one is little bit tricky. Here
V2.
V1 not V2. V1 by V2 raised to the power what? Gamma minus 1. See, for this one, generalized equation state is also applicable. Other than generalized equation of state, these 3 equation of states also there.
Okay.
And here, what is the meaning of gamma? Gamma stand for what? Adiabatic index or isentropic index. Where gamma means what? We have seen already. And why we have given the name gamma, adiabatic index or isentropic index? Because it is the index for isentropic process or adiabatic process, and that's why we have given the name adiabatic index or isentropic index for the gamma. So gamma stand for what? Adiabatic index. That is what the name we have given.
Yes.
Or what we will say?
Isentropic index.
Isentropic index. And what is the relation for gamma? Can you tell me what will be the relation for gamma? Gamma will be equal to what?
Cp by Cv.
Gamma is equal to what? Cp by Cv. Ratio of specific heats.
Yes.
That is what we have seen for the gamma. Now C point will be what? What will be C point? PV diagram.
TS diagram.
And D point will be what? TS diagram, temperature entropy diagram. Now try to see the scenario here, how we are going to approach here further. So pressure volume diagram, and then next will be what? temperature entropy diagram, and we have seen we generally prefer to draw PV and TS diagram side by side. Now for here we will have a expansion. So this will be what? A expansion, isothermal expansion. Observe the things here carefully. So this line will indicate what? Isothermal expansion. So 1 to what? 2. So this will be what? Isothermal what? Sorry, not isothermal, my mistake. It is what?
Expansion.
Isentropic expansion. Expansion means increase in pressure. Sorry, expansion means what? Decrease in pressure, increase in volume. Now in case of the compression, it will be what? Reverse of that?
Yes, decrease in volume, increase in pressure.
So this is what our compression scenario.
Yes.
1, decrease in volume, and here what is happening? Increase in pressure. Now in TS diagram, for isentropic process, constant entropic process, how will be the TS diagram? Horizontal line, vertical line, or curve?
It will be, sir, vertical line.
It will be what? Vertical line. And why vertical line? Why will be the vertical line? It must be what? Entropy constant. Entropy constant means what? Yes, constant here. So because here T, yes. So it must be what? So I am now drawing two scenario here. What I am drawing? I am drawing two scenario. In one scenario, temperature is increasing. So in this scenario, temperature is what? Increasing. Now in this another scenario, what happened to the temperature? Reverse of the what? First scenario. So here, just observe here, see the arrow?
Yes.
Here 1 to 2. So in this second scenario, temperature is decreasing. So out of this, what is this first scenario? This first scenario is what? Compression or expansion? This first scenario?
This is a heat addition to this.
So first of all, remember one point. What is the meaning of isentropic process? What will be the heat transfer for isentropic process? Tell me. What is the heat transfer for isentropic process? What will be the relation for heat transfer for the isentropic process?
Heat transfer.
What will be the heat transfer for isentropic process?
Q is equal to 0.
Q is equal to what?
0.
Q is equal to what? 0. Means if I call you early in the morning, 5 o'clock.
Yeah.
And you said quickly, what is heat transfer for isentropic process? 0.
0, yes.
It will be what? 0. And that's why entropy is remaining constant here.
Okay.
So now tell me out of this one. So remember, that's why entropy is remaining constant. So no heat transfer, no heat addition, no heat transfer, no heat rejection.
Yeah.
So tell me this first scenario will be what? First scenario will be what? Heat addition or heat rejection? This scenario, this currently I have highlighted this scenario. What is happening here in this scenario? Temperature is what?
Increasing.
In which case temperature is going to increase? In case of compression or in case of expansion?
So in case of compression.
In case of compression. So that's why this scenario is what?
Compression.
Compression. And this scenario in case of expansion, what is going to happen?
Heat is going to decrease.
What is going to decrease?
Heat.
Heat.
I mean temperature.
And don't get confused with the heat and temperature. Temperature is a property of the system. It depends on the internal energy.
Yes.
Heat transfer is a energy transfer due to temperature difference. What is meant by heat transfer? Heat transfer is a form of energy transfer. It is due to what? A temperature difference between system and surrounding. Remember this point. Don't get confused with the temperature and heat. A lot of people get confused. So in case of thermodynamic, few things are very, very straightforward. First thing is heat. Heat transfer is a what? Energy transfer due to temperature difference. Temperature is a property of the system. It depends on what? Internal energy. More internal energy means more temperature. So temperature is a measure of Means what? It is a, we will say hotness or coldness. It is a measure of what? We will say it is a measure of hotness or coldness. Heat transfer is what? It is a energy transfer.
Energy transfer.
See the difference. Temperature is what? Measure of hotness or coldness. Means more internal energy means more temperature. So remember this point. Don't get confused here. So please draw
Yes.
PV and TS diagram. And you got it now. Why? In case of the compression, temperature is increasing. Means if you compressing the here and no heat transfer is there, what is going to happen automatically?
The temperature will rise.
Temperature will rise. Normal tendency. In case of expansion, we are not doing any heat transfer. What will happen to the temperature? It is going to reduce.
Yes.
So please draw this PV and TS diagram. Write down this discussion. So what will be the our E point will be here what? Boundary work relation.
Boundary work relation.
So E point will be what? Boundary work relation.
Yeah.
And what will be the boundary work relation? Q minus W
is equal to delta V, delta U.
Okay, no, it is not a boundary work relation. It is a first law relation. Here what is the boundary work relation? W, we will see. P1 V1, see this one, P1 V1 first minus P2 V2 divided by what? Gamma minus 1. This is one relation of the work done.
Okay.
And then next relation is what? MR T1 minus T2 divided by what? Gamma minus 1. Here we will have in kilojoule. Here is also we have in what?
Kilojoule.
So please write down this relation of the work done.
So in this case, this T1 and T2 what we are taking. So in that case, if we are doing a numerical, so T1 will be always the higher temperature, correct?
If it is expansion, sir.
Okay.
If it is expansion,
clauses in this.
If it is expansion, T1 higher, T2 lower. In case of the compression, the reverse thing will be there.
I mean, whatever would be the higher one, then we have to take it in the higher one, right?
No. See this one. T1 means what? It is not like this. Here, we have to see sign convention also, na? Initial minus final. That's what we have written. Suffix 1 stand for what? Initial. Now, what will be the our F point? F point will be what?
Will be first law relation.
First law relation. And what will be the first law relation? Q
minus W is equal to delta U. So Q is 0. W is equal to delta U.
So Q is what here?
0.
0. So what we can say? Minus W is equal to what? Delta U.
Delta U.
So W will become what? So
minus of delta U.
So minus of and delta U means what?
M
CV
into PV into T1, T2 minus T1.
T2 minus T1.
Yes. It will be now T1 minus T2.
So W will become what? MCV T1 minus T2. Remember
minus
T1 means
T2.
initial temperature.
Yes.
T2 means final here. 1 stand for initial, 2 stand for final.
Okay.
So please write down this one. Now what will be the our next point?
Change in entropy relation.
So what will be the change in entropy relation we can say?
Is equal to delta S. Change in entropy will be 0, no sir?
So no need to write down any relation. In sleep also, what will be the change in entropy? For isentropic process, it must be 0. Okay.
At least two formula reduced.
So in sleep also, sometimes I have observed a lot of students, what they are going to do, they are going to write down the relation of change in entropy, these relations of change in entropy, these relations of generalized relation of change in entropy, they are going to apply for isentropic process. Okay. So in sleep also, never try to apply the relation of change in entropy.
Yes. Done, sir. Now last.
What is our last process?
Sir, that one was just written the name of it. Polytropic process.
What is the last one?
Polytropic process.
Polytropic process. So fifth one is what? It is our general category. So give the fifth heading. Polytropic process. Here everything is general.
Okay.
Polytropic process, give the heading. Fifth process, polytropic process. If any process is not out of the above four processes that we have studied earlier, then that process is what? Polytropic process. Now here A point will be what? Condition. So here this condition will be what? No specific condition.
Okay.
So write down here. Here we don't have
any specific condition.
Not any specific condition. No specific condition.
Okay. Yes, sir.
Now then after that, what will be the B point? Equation of state. Here whatever the equation of state we have seen for the isentropic process, similar equation of state will be here also. See, there we have seen P1 V1 raised to the power gamma is equal to P2 V2 raised to the power gamma. But here instead of that, here we will have P1 V1 raised to the power n is equal to what?
P2 V2 raised to the power
n. Here n will come. Second one will be what? T2 by T1 will be equal to what?
T2 by T1.
P1 raised to the power what? N minus 1 by what?
N.
N minus 1 by what?
N minus 1 by N.
N. Okay. And then third one will be what? What will be third one?
T2 by T1 is equal to V1 by V2 N minus 1.
N minus 1 means here we replace. Now there in case of the isentropic process or adiabatic process, that index, what is the name we have given to that index? Tell me.
Isentropic index or adiabatic index.
Because that process is what? Isentropic process or adiabatic process. Now here tell me this index n, what is the name we can give this index n?
Polytropic index.
Yes, polytropic index. So where n stand for what? What is the meaning of n? N stand for what? Polytropic index.
Yeah.
Okay. If it is an expansion process, then we will say index of expansion.
Okay.
If it is what? Polytropic expansion process, then index of what?
Expansion.
Okay. If it is a compression process,
index of compression.
Index of what?
Compression.
Compression. Please write down this discussion.
Yes. So T2 by T1 is equal to V1 by V2.
Yes, I have made the mistake here. So here V1 by V2. Now our C point will be what? What will be our C point?
Diagram, sir. PV and P.
PV diagram. and D point will be what? TS diagram. Pressure volume diagram, and TS means what? Temperature entropy diagram. And generally we try to draw this one side by side.
Yes, sir.
So PV diagram, and then here we will have what?
TS diagram.
TS diagram. So here in this case we will have a first of all expansion, polytropic expansion. Expansion means what? What will be expansion? Decrease in pressure, increase in volume. So this is what our polytropic expansion. So this process indicate what?
Expansion.
So this process indicate what? Expansion. Then we will have what? This scenario will be what? A compression scenario.
Decrease in volume, increase in pressure.
So this scenario will be what? A compression. And here TS diagram we can't say. So here TS diagram not specific. We will see how to draw the TS diagram for the polytropic process during the numerical. So PV diagram and TS diagram. Then E point will be what?
Boundary work relation.
Boundary work relation. So try to see the scenario here. How will be the boundary work relation? So W, same as the isentropic, but here only difference in isentropic, what is the relation of work done? P1 V1 minus P2 V2 raised to the power what? Sorry, divided by what? Gamma minus 1 instead of gamma. Here what we will have?
N minus 1.
N minus 1. Then relation of W will be another relation. MR T1 minus T2 divided by what? Instead of gamma, here we will have
Minus 1.
and unit of work done will be in what?
Joules. Kilojoules.
Kilojoule, not a joule. We will prefer generally, if you take a joule, it will be smaller unit. So term will be very, very big. So instead of that, we will prefer kilojoule.
Okay.
Now what will be our F point?
First law.
First law relation.
Yes.
So what we can say, what is first law relation? Q minus W
is equal to delta U.
Delta U. So what will be the relation of Q will become here then? Delta U plus W.
Yes.
Means whenever we want to find out heat transfer for a polytropic process, we will use this relation. Q is equal to delta U plus W.
Okay.
Please write down this relation. Then G point will be what?
Entropy relation.
Change in entropy relation.
Yeah.
So what will be the change in entropy relation? Here we will use, see, this is a generalized processor. So delta is generalized relation. MCV ln
T2 by T1
plus
R ln V2 by V1.
V2 by V1.
Yeah.
So generalized one.
Similarly with for the pressure also.
For the pressure also delta S M CP ln of what? P2 by P1.
T2 by T1.
T2 by T1. Okay, I'm wrong. So here we will have what? T2 by T1 minus R into ln P2 by P1. Okay, it must be in what? Kilojoule per Kelvin. Here also in what? Kilojoule per Kelvin. Okay, please write down this relation of change in entropy.